Good evening, Loughton. The end of everything. I'm going to be talking about the fate of the Earth, the fate of the Sun, the galaxy, and ultimately the fate of the universe. So if you'll forgive me paraphrasing Buzz Lightyear, we're going to be going to eternity and beyond. So after a little prologue, I'm going to be talking about what's going to happen to the solar system, Earth, Sun, and the rest of the solar system. I'll be looking into the far future and the fate of stars and galaxies, and then looking into the far, 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 far future and the ultimate fate of the universe. And so as not to leave you too depressed at the end of this evening, I'm going to finish with a slightly more upbeat epilogue. So you've already had 3 weeks ago the beginning of everything, so there's no need to go through that. In short, it took 3 minutes to make all of the hydrogen in the universe. And since then, the stars have been converting that hydrogen into helium and carbon, nitrogen, oxygen, and the heavier elements. In this talk, I'm looking into the future, and in order to keep track of where we are, I'm going to use this timeline set of boxes at the top of the screen there. Each box means 10 times further into the future than the previous. So I'll be looking, for instance, 1,000 years into the future, 10 to the 3, 10 to the 4, 5, 6, a million years into the future, 10 to the 7, 10 to the 8, 10 to the 9, a billion years into the future, and so on. And there we have on the right-hand side, 10 to the 12 years, 1 trillion years into the future. And I'm indebted to the work of Adams and Laughlin, who published a paper at the turn of the millennium in which they laid out the timescales on which various astrophysical events are likely to occur, and I've used the events in that paper to try and get my slides into the right order. So we're not going to bother with 10 to the 1, 10 to the 2, 10 to the 3. Let's assume we get global climate change under control. Let's assume we don't end everything in nuclear war. The next thing that we can think about is that we know that in 10 to the 4 years' time, things are going to change. The pole star will change. Because of the precession of the Earth's axis, indicated there on the left-hand side, there's a 26,000-year cycle whereby the tilt of the Earth doesn't change, but the direction in which it points sweeps a large circle on the sky. So at the moment, our axis is pointing close to the star Polaris, which we currently call the North Pole Star. But in 10 to the 4 years, about 11 to 12,000 years, it's going to change. And it'll be the star Vega on that sort of timescale. So we'll have a much brighter pole star. Some people seem to think the pole star currently is quite bright, but it's only magnitude 2 or so. So apart from the fact that in 10 to the 4 years' time, it's going to be a lot easier for Boy Scouts to point out which way is north, there are other consequences to the pole star changing. At the moment, the Earth's tilt is such that we are nearer to the Sun during northern winter. When we are in January, we are slightly closer to the Sun, and so there's a mitigation of the seasons. But if you think of the Earth tilting the other way, tilting towards Vega, then we're going to be nearer to the Sun during northern summer when the axis is tilted towards the Sun. And so these seasons are going to be a little bit exacerbated. So there will be variations in the Earth's climate due to changes either in the Earth's spin or the Earth's orbit, and collectively these changes are called Milankovitch cycles, and we'll be seeing that again shortly. On a timescale of 10 to the 5 years into the future, the Voyager space probes launched in the 1970s are going to pass nearby star systems. So, for instance, if we look at this particular diagram, at the top we have Voyager 1, and on this sort of timescale, Voyager 1 will be passing through the star system Gliese 445. At the bottom of the diagram, Voyager 2 is heading off in a different direction and will pass through the system Ross 248. Pioneers 10 and 11 were launched earlier, but they're travelling a little more slowly, so they'll take a little longer to travel to the nearby stars. Pioneer 10 on the right is heading off in the direction of Aldebaran, and Pioneer 11 on the left of this diagram is heading off towards the centre of our galaxy. On a same timescale of 10 to the 5 years into the future, we know that there will be global changes to the Earth's climate because we're going to enter another ice age. Ice ages tend to come and go on timescales of order 100,000 years or so. And the Earth entered an interglacial or a warm period relatively recently, and so we can say that the next ice age is due on a timescale of order 100,000 years. We can't be too precise, but this is another manifestation of Milankovitch cycles. It's to do with subtle changes in the Earth's orbit around the Sun. Now, we've known for a long time that the Earth is slowing down. We've known that since we've had atomic clocks and can measure the rotation rate of the Earth accurately. And in a talk I give about why we need to add leap seconds, at the moment we're adding a leap second perhaps once every few years. But as the Earth continues to slow down because of the tidal effects of the Moon, it will be necessary to add leap seconds not once every few years, but we would need to add a leap second essentially every day. In other words, on this timescale, the rotation period of the Earth, instead of being 24 hours, will be 24 hours and 1 second. Still on a timescale of order 10 to the 5 years or so, we know that some stars are going to go supernova. It's very difficult to predict exactly when. So for instance, Eta Catenae is a definite candidate. It's there in the southern hemisphere. It's already produced a nebula around it because it's been shedding its outer layers for many thousands of years, and it's looking very unstable. So it's a prime candidate to go supernova. It's a very massive star and it appears to be unstable. Perhaps it'll be beaten to the punch by Betelgeuse, which will be visible, of course, from the northern hemisphere. Here's an astrophoto of the night sky seen from Prague, but with Betelgeuse artificially brightened to show what it might look like when it eventually goes supernova. It'll probably be bright enough to be visible during the day for a while. Because Betelgeuse is only 600 light years away, that's relatively close, and so it will be quite a spectacular supernova when it decides to go. It might go before 10 to the 5 years, we can't be absolutely sure. There are some stars that are even more dramatic deaths than supernovas. So for instance, Wolf-Rayet stars, and this is Wolf-Rayet 104, an artist's impression. It's 7,000 light years away, and it sounds like, well, nothing much can hurt us at that distance. But its death, when it does happen, might result in a radiation burst even more powerful than a supernova. And that's because of these jets that you can see in this artist's impression. Wolf-Rayet stars have very rapid rotation systems, and they can produce these jets heading off in the polar regions. And if the jets happen to point towards Earth, then when the star dies, it can produce a gamma ray burst with very intense gamma rays heading off in the jets. And if those jets happen to be aligned towards Earth, that can be really bad news for us. We're not too sure, but we don't think Wolf-Rayet 104 has a jet pointing in our direction, but again, it's difficult to be absolutely sure. On a timescale of 1 million years into the future, all the stars in the Milky Way are rotating around the centre of the Milky Way and are currently being mapped out by the spacecraft Gaia. And Gaia has found that there are some stars, although they're in independent orbits around the Milky Way, they may happen to come close to our star. And in 1 million years, it's calculated that Gliese 710 is going to come very close. So close it will actually enter inside our Oort cloud. The Oort cloud extends for some rather large distance between us and the nearest stars. It's of order a light year or so in diameter, and consists of trillions of small icy bodies. So if a star like Gliese 710 comes close enough to actually enter the Oort cloud, it's going to disturb a very large number of these small objects, and a number of them are going to come raining down into the inner solar system. And almost certainly will result in naked eye comets for perhaps millions of years. It's interesting to note that for a while at least, our solar system will have 2 suns, just like other worlds that we can think about. Still on a timescale of 10 to 6, am I showing a picture of meteor crater because we can expect an impact like this once every million years? Well, no, not really. I'm showing this picture because, one, it's something to note that wasn't it lucky that this impact just missed the visitor centre. What a stroke of luck that was. But no, the reason we're showing this in 1 million years is that on that sort of timescale, we can expect the weathering systems of the Earth to actually erode meteor crater, such that anything older than that would not be visible. Meteor crater is only perhaps tens of thousands of years old. Anything older would not be visible. The moon, you say, well, no atmosphere, so surely that will not be a problem. Well, anything on the moon will still be eroded by constant bombardment from micrometeorites. So we look at the footprint of the astronauts from Apollo and we think they'll be there forever with no atmosphere to erode or weather them. But no, with micrometeorites continually raining down, eventually all evidence of the Apollo landings will be erased. On a timescale of 10 to the 7 years into the future, well, what's going to happen to Pioneer 10? We've already said that it will be passing through other star systems. But on a timescale of 10 to the 7 years, the plaque, which is there on the side of Pioneer 10 and Pioneer 11, the plaque indicates the home of the Pioneer spacecraft. There's a pulsar map on the left and an indication on the bottom that this particular space probe came from the third rock from the Sun. On a timescale of 10 to the 7 years, the plaque is going to get eroded because of Pioneer's passage through interstellar space. Interstellar space is not empty, it's full of tiny dust particles, and so after many millions of years flying through interstellar space, the plaque is going to get pitted and eroded by all of impacts from these tiny dust particles. So if any species does pick up Pioneer 10, remember it's flying through different solar systems, perhaps once every few tens of thousands of years. So by this timescale, it will already have passed through perhaps many hundreds, possibly even thousands of solar systems. If any species does pick it up, on a timescale less than 10 to the 7, they might be able to read the plaque and tell where it came from. On timescales greater than 10 million years or so, it is probable that they'll not be able to work out where Pioneer 10 or Pioneer 11 came from. On a timescale of 10 to the 8 years, we think Saturn's rings are going to change. But first we might ask, where did they come from in the first place? Did the moon, a moon similar to Mimas for instance, make Saturn's rings? If we take something about the mass of Mimas and imagine it getting pulverized, we end up with something which is about the mass of Saturn's rings. So perhaps that's their origin. But when we look at a moon like Mimas, we might think to ourselves,
that's no moon, it's a space station.
Because it does seem to have a very large crater there bearing a certain resemblance to the Death Star. But simulations have been done to try and work out the origin of Saturn's rings. If we take a moon with a mass similar to Mimas and pulverize it and then allow gravity to do its stuff, how long does it take until all the debris from that one little moon gets smeared out into a ring system? You might assume that if you pulverize a moon, it will simply produce a cloud which takes a long, long time to disperse. But this simulation, if you look at the time in the bottom right-hand corner, you can see that the debris of the moon ends up as a ring system in a matter of days and weeks. It doesn't take a long time at all for the ring system to disperse and for debris to occupy the entire orbit of the original moon. Now, if this happened many millions of years ago, it's calculated that because all of the individual particles in the ring systems are continually bumping into each other, their orbits will decay and the individual particles of the ring system slowly migrate inwards year after year after year. And so now that's the ring system that we know and love, that we see at the moment. But this process of migration of the particles of the ring system is ongoing. It hasn't simply stopped, it will continue. And it's been calculated that on this sort of timescale, 10 to the 8 years into the future, all of the particles of Saturn's ring system will have migrated inwards and rained down onto the surface of Saturn. And so the ring system will be no more. So for those of you who enjoy the spectacle of Saturn's rings, Make sure you get your viewing in now, because in another 100 million years, you won't have the opportunity. Still on a timescale of order 10 to the 8 years into the future, 100 million years into the future, because we see models of the solar system like orreries or tellurians of the Earth-Moon-Sun system, it's tempting to think of the solar system as working by clockwork. But we have to remind ourselves that on timescales of many millions of years, the solar system is in fact chaotic. It is not predictable. Yes, we can work out where the planets were thousands of years ago, and we can work out where they will be thousands of years from now. So, for instance, we can work out what was in the sky to try and work out what the Star of Bethlehem was. But we can't simply wind the clock backwards or forwards indefinitely. If we attempt to do that many millions of years into the future, we find not only do we not know where the planets are going to be in their orbits, we're not even sure how many planets the solar system will have in 10 to the 8 years. It could be that Jupiter decides to eject one of the planets in the solar system. We think that probably has happened in the past. It may well happen again in the future. So don't be fooled by a model like an orrery, which makes us think that everything works by clockwork. Just like the weather, the solar system is chaotic. Still on a timescale of 10 to the 8 years into the future, that's roughly speaking the length of time it takes the galaxy to rotate once. That's where the Sun is at the moment. We are sitting in a relatively unpopulated part of the galaxy, sitting in between two spiral arms, a relatively low density region. But on a timescale of 10 to the 8 years, it's been calculated that we are likely to move into one of the spiral arms of the Milky Way. And so we will find ourselves in a much higher density region of the Milky Way. We will have a lot more stellar neighbours. So what are the consequences of having lots of stellar neighbours? In other words, many stars within a distance of, let's say, 10 light years, whereas at the moment we've got relatively few neighbours within 10 light years. We've already seen one of the consequences, and that is if stars get too close to us, they can disturb the Oort cloud and they can produce asteroids and comets raining down into the inner solar system. Some of them will hit Earth. And if we have a look, for instance, at the historical record of extinctions of species as a function of time, we find a number of spikes, quite a few spikes over the last 500 million years. So on timescales of order 10 to the 8 years or so, we find that we are getting extinction level events. The last one was at the so-called KT boundary, the boundary between the Cretaceous and the Tertiary eras. That's the asteroid that impacted and effectively killed all the dinosaurs and allowed us to evolve as a consequence. So we think that on a timescale of 10 to the 8 years, again, we can't predict it exactly, but certainly it's likely that on this sort of timescale, we are going to find ourselves impacted again. So this, of course, is just an artist's impression of what that might look like. A huge lump of rock heading towards, well, it looks like it's heading towards Italy. That's definitely bad news for Italy. But if the rock is big enough, it's bad news for the entire planet. Species will be exterminated if the rock is large enough. The real question is, of all the species that will be exterminated, will we be one of them? Well, we've got a little bit of time to figure that out. We can think about plans for mitigating. We can get the Bruce Willis scenario of send somebody up there with nukes and see what we can do, or we have the option of DART to try and nudge it off its course if we can find one of these things early enough. A second consequence of having lots of stellar neighbours, apart from disturbing the Oort cloud, is that a lot of stellar neighbours means there's always the possibility of one of our neighbours will go supernova. At the moment, we haven't got any high mass stars close enough to cause a problem. A supernova within 100 light years would be a danger to Earth from the amount of radiation that would be produced. And it's been calculated that a supernova within 20 light years of us might conceivably produce enough radiation to end all life on Earth. Remember, Betelgeuse is at 600 light years or so, and that is considered to be a safe distance. But if we've got lots of neighbours, some of them might be high mass stars which will end their lives as supernova. If that sounds a little bit alarmist, bear in mind that it's happened before. We think that supernova within 100 light years have gone off because when that happens, a deposit of a particular isotope called iron-60 would be left in the Earth's sediment. Iron-60 is only made in a supernova, it's not made by any other process as far as we know. And iron-60 is radioactive such that it only lasts for a few million years. The iron isotope, after a few million years, turns into cobalt, which then turns into nickel. But we do find this isotope in Earth sediments. And it can't have been there for a long time because it decays into cobalt and then nickel. And it does so after a few million years. So if we find iron-60 in Earth sediment, it must have arrived relatively recently. It can't have been there since the beginning of Earth's history billions of years ago. So it looks like the existence of this isotope in Earth sediments tells us that there have been supernova close enough to deposit this particular isotope, and it must have been not that many million years ago. And so if it's happened before, it can happen again. All of this time, the moon has been tugging on the Earth, and the distance from the Earth to the moon will increase because the moon is pulling on the Earth and slowing the Earth down. The moon is effectively robbing the Earth of some of its angular momentum, some of its spin, and as a consequence, increasing the size of the moon's orbit. So the Earth will now have a day which is now 25 hours long. It's now ridiculous to think about adding leap seconds to try and keep the rotation of the Earth synchronized with our clocks. We have to give up that idea completely. But the most important consequence is that the distance from the Earth to the moon will increase and will, at this sort of timescale, be so large that it will be impossible to have a total eclipse of the sun. At the moment, we're lucky enough to have this coincidence that as seen from the surface of the Earth, the disk of the moon is just about big enough to cover the disk of the sun. Sometimes it's a little bit too far away and we get an annular eclipse, but total eclipses can happen. But on timescales of order 1 billion years or so into the future, the moon will have moved further enough away such that a total eclipse cannot occur. We will still get annular eclipses, we will still get partial eclipses, but no more total eclipses seen from the surface of the Earth. But a rather more serious consequence of the moon moving away from the Earth is the fact that the moon has had a stabilizing influence on the tilt of the Earth, this so-called obliquity. The angle between the Earth's axis and the vertical, defined by the perpendicular to the ecliptic, that hasn't changed much as far as we can tell in recorded history. It's only changed by about 1 degree either side of 23.5 degrees. The cartoon on the left shows the sort of variation that we can deduce from historical records. So in other words, the seasons of the Earth have been quite stable. But if the moon moves further away, it's been calculated that if it moves, say, 25% further away, then the moon will no longer stabilize the tilt of the Earth, and the tilt of the Earth could then change erratically, which would then, of course, result in wild variations in the Earth's climate, because our seasons are dictated by that particular tilt angle. So again, changes are on the way. Regardless of man-made changes to the climate, there will be drastic changes to the climate on these timescales into the future. Still on a timescale of 10 to the 9, billions of years into the future, what's going to happen to Voyager's gold disk? Well, eventually the gold disk will become unreadable. Remember, we said the Pioneer plaque will become unreadable on timescales of order 10 to the 7 years because of its flight through the interstellar medium. Voyager's gold disk will survive a bit longer, mainly because it's protected behind this cover disk on the left-hand side, protecting the gold disk itself, which is a phonogram giving us welcome messages and sounds from planet Earth. So although it's a good idea to have a cover that protects the gold disk, unfortunately, it is the cover that contains the instructions for how to play the disc. So we have to assume that after 10 to the 9 years, again, Voyager will have passed through thousands upon thousands of solar systems. If it's picked up on this sort of timescale, then anybody who reads the disk will be able to read the instructions and figure out what it means and see the pulsar map on the left-hand side. On timescales greater than 1 billion years into the future, Voyager itself might survive, but the disk will be unplayable in the sense that we'll no longer be able to read the instructions. Maybe they can figure out how to play the disk, even though the instructions have been completely eradicated by the pitting, the erosion produced by the interstellar medium. On timescales of billions of years into the future, our sun is going to change. As it heads towards its red giant phase, the luminosity is going to slowly ramp up at the rate of something like 10% increase in luminosity for every billion years. That's going to drive the surface of the Earth up to a relatively balmy 80 Celsius. So even before the sun becomes a red giant, the oceans are going to boil dry and the Earth will be uninhabitable. Going underground is not going to help. We're going to need to leave the Earth until it cools off a little bit. But we know that the sun is going to go into a red giant phase and it will expand until the surface of the sun is, roughly speaking, where the orbit of the Earth is. So it sounds like the Earth will become engulfed in the atmosphere of the sun. And it sounds like, well, yeah, that sounds like it could be a problem. But there are two schools of thought. One, that the Earth will be engulfed, and the other possibility is, well, maybe it won't. We know the sun is going to become a red giant. We know the red giant will probably, based on our knowledge of other stars, end up being the size of the Earth's orbit. However, the Earth is going to move because as the sun expands, very strong solar wind will result in the sun losing quite a lot of its mass. If the sun loses mass, there's less gravity pulling on the Earth, which means the orbit of the Earth will expand. And this cartoon on the left-hand side shows that as the sun expands, the Earth actually moves away from its original position. So yes, the sun will expand until it engulfs the original Earth orbit, but the Earth won't be there anymore. The Earth will then have a new orbit, perhaps some distance away, such as the distance of the current Martian orbit. So the Earth won't necessarily get engulfed. It'll still get rather warm, but it won't necessarily get engulfed and disintegrate within the sun. It might conceivably survive. Once the sun has gone through its red giant phase, it'll slough off its outer layers and then become a white dwarf, a very dense star about the size of the Earth. This is on a timescale of many billions of years into the future. At some point, the Earth will cool off. Maybe we can return at that point, having had the Earth go through a rather warm phase. But we have another problem to contend with, and that is that the Earth is going to lose its magnetic field. As the core of the Earth cools, it'll lose its magnetic field because we need a molten core to produce the dynamo that generates the magnetic field. And the Earth's core is not kept warm by the sun, it's kept warm by radioactive decay of elements that are in the Earth and have been there for billions of years since its formation. Eventually, the radioactive decay of those elements is not enough to keep the molten core molten. And once the core solidifies, we no longer have a dynamo, we no longer have a magnetic field. And so we'll be exposed to radiation from the sun. Perhaps that's not so important now that the sun has become a white dwarf, but we will be exposed to cosmic rays, and that will be a problem for us. They say bad news comes in threes. If we survive the sun going through its red giant phase, if we survive the Earth losing its magnetic field, then there's a third potential problem on the horizon. And that is the Andromeda Galaxy is going to collide with the Milky Way, still on these timescales of quite a few billion years into the future. Here's an artist's impression of what the Andromeda Galaxy might look like on a timescale of 3.7 billion years into the future. We won't need a telephoto lens to get a nice image of the Andromeda Galaxy. We'll need a wide-angle lens to get it all in. It'll fill our entire sky. And as the Andromeda Galaxy passes through the Milky Way, it'll be impossible to tell which star belongs to the Milky Way, which star belongs to Andromeda, and there is going to be a riot of new star formation as the two galaxies pass through each other. It's very unlikely that any star will collide with the Sun. In fact, it's very unlikely that any star will collide with any of the stars in either galaxy, even though both have hundreds of billions of stars in them. The gas and the dust will mix, and that's producing the new star formation, but it's unlikely the Sun is going to be hit by anything coming in from Andromeda. If the Sun does get pulled out of the Milky Way, well, the planets will simply go with it. So that's not a cataclysmic event as far as the Sun is concerned. Eventually the galaxies will pass through each other and come out the other side, and then they will settle down with the two nuclei, the centre of the Milky Way and the centre of the Andromeda Galaxy, both of which have supermassive black holes in them. Eventually those two supermassive black holes will orbit each other, and a long time into the future they will end up merging together. On a timescale of 10 to the 11 years into the future, the dance between the Moon and the Earth finally comes to an end. The tidal effects will lock the two together. In other words, one day, the rotation period of the Earth, will become the same as 1 month, the length of time it takes the Moon to go round the Earth. The Earth will become tidally locked to the Moon in much the same way as the Moon is tidally locked to the Earth. So just as we only see one face of the Moon, eventually the Moon will only see one face of the Earth. At some points on the Earth, you will see the Moon in the sky fixed in place. From other points on the Earth, the Moon will simply never rise above your horizon. And this, by the way, that looks like a photoshopped image on the right-hand side is a genuine image from the Deep Space Climate Observatory. It looks odd because we're seeing a full Earth and we're seeing the far side of the Moon, not the usual near side of the Moon, as it was taken from some distance away. We've now reached 10 to the 12 years into the future. We're looking at some of the galaxies in the local group. There's the Milky Way in the centre, surrounded by a lot of small satellite galaxies, dozens, hundreds, possibly more that we haven't been able to find yet, but certainly a large number of small galaxies. We've already said that the Andromeda Galaxy M31 is going to end up merging with the Milky Way. Well, ultimately the same will be true of M33 Triangulum, and indeed all of the small galaxies in the entire local group will merge into one mega galaxy. It won't be a spiral galaxy as indicated by this little icon. It'll probably be a very large elliptical galaxy. So if all of the galaxies in the local group will merge under the influence of gravity, what's going to happen to more distant galaxies? Well, we know at the moment that if we want to look out into the universe, we can see galaxies receding from us at great distances and indeed at great speeds. Back in COVID lockdown, I actually imaged a quasar, which is a galaxy with a very bright nucleus. I imaged one that's actually so far away, it's receding from us at twice the speed of light. But even so, it is still possible to image such galaxies. This quasar that I imaged without using a telescope, just a camera on a tracker, this particular quasar is at a distance now of about 25 billion light years, and the light travel time from this object was about 12.5 billion years. Remember, the universe is 13.8 billion years old, so the light from this particular galaxy has been travelling for something like 90% of the age of the universe. So that is possible to do now, and if we look on the right hand side, we see a more detailed image. This is a Hubble Deep Field, the Hubble Ultra Deep Field, where they've looked at a tiny patch of sky and they see thousands of galaxies. There's also a couple of stars in this image because a couple of stars happen to be in the same line of sight. These two stars are in our own Milky Way. Everything else in the image are more distant galaxies. But although it's possible now to image galaxies at great distances, even those receding faster than the speed of light, eventually on a timescale of 10 to the 12 years, The universe will continue to expand for all of this time, and on this sort of timescale, every galaxy at distance will be so far away they will be impossible to image. So we can imagine, what if a civilization came into existence on a timescale of 10 to the 12 years into the future? What if they built themselves a Hubble Space Telescope or equivalent, regardless of what they call it? And what if they pointed into the distant universe and took a picture like the one on the right? Well, because the galaxies will be so far apart at this time scale, what they will see is absolutely nothing other than the stars in their own galaxy. A civilization that comes into existence on this time scale, when they look out into the universe, will come to the conclusion that the entire universe is just their own galaxy, because they will not be capable, it's nothing to do with the technology of the telescope, they will not be capable of picking up light from more distant galaxies. So it's sobering to realize that we can see maybe 1 trillion galaxies in the observable universe, but that won't always be possible. Eventually, the universe is going to run out of hydrogen. I said in the beginning of everything that it took 3 minutes to make all the hydrogen in the universe. But after many trillions of years, it's starting to run out. And if you run out of hydrogen, you can't make new stars. Well, some scientists will argue, okay, you really do need hydrogen to make stars, but isn't it actually possible to make stars out of other stuff? Can you make stars from heavier elements? Some people have tried doing some calculations and they seem to think that maybe it's possible to make stars out of heavier elements than hydrogen, and you end up with stars in which you have nuclear reactions at the core, you have fusion reactions generating energy, but the surface temperatures are orders of magnitude lower than, for instance, even a red giant. A red giant would have a surface temperature of 3000 Kelvin or so. Maybe you can end up with a star with a surface temperature of only hundreds of Kelvin. The star would be cold enough for ice to form in its outer atmosphere. Frozen stars. Now, yeah, okay, if you're thinking of Disney's version of a frozen star is that picture on the left-hand side. That's not what I'm talking about. So if that's the picture you've got in your head, then let it go, because what I'm talking about are stars with nuclear reactions at the core, but ice in the upper atmosphere. Some scientists say that's possible. Many scientists say, no, you really, really do need hydrogen to make new stars. It can't really work any other way. So to figure out what the consequences of that are, we have to think about the cosmological model in terms of what we think is happening to the universe as a whole. If we want to push that red rectangle any further beyond 10 to the 12, we have to ask ourselves, on the biggest of scales, what's happening to the universe. So we're just going to have a little aside for a couple of minutes and ask ourselves what the universe is doing. This is a graph of the size of the universe on the vertical scale versus time along the horizontal. So that's where we are now. The size of the universe is just an arbitrary scale. Let's call it 1 at the moment. Various coloured lines indicate what the universe might have done in the past and might do in the future. Notice that depending on what we think the universe is doing, the age of the universe will be a function of, or dependent on, which model we have for how we think the universe is behaving. And the different coloured lines here are dependent on how much matter and how much energy there is in the universe. So in other words, if there was a huge amount of matter in the universe, then we would follow the orange line. And that would mean that there's so much matter in the universe, gravity would grab hold of all that matter and would stop the universe expanding, and the expansion of the universe would start to reverse, and we'd have a big crunch sometime in the future, a so-called closed universe. We thought that might have been a possibility some decades ago, but now we've got a much better idea of how much matter and how much energy there is in the universe, and we don't think we're on the orange line. When I was young, we had an inkling that we might be on the green line. But now we think actually the most likely thing is we're on the red line. That's the amount of matter and energy in the universe, our best guess so far. And that means we are looking at the red line. Notice that not only does the universe continue to expand, it also is accelerating. The gradient of that red line is increasing with time. As far as we can tell, the universe is expanding and accelerating its expansion. There's nothing that we can see out there that makes us think that the universe is going to turn over and start contracting again. So that's something to bear in mind. We don't have to worry about the universe coming to an end in the sense of a big crunch. It looks like the expansion will continue forever. Perhaps we will learn something in years to come that will change our mind, but that's the model we have at the moment. So in order to make any progress at all, rather than be here until gone midnight, I've changed the numbers at the top of the screen. Now each box in the timeline means 1,000,000 times further into the future, not simply 10 times further into the future than the previous box. And I don't know what adjectives we're going to use, but we've got a zillion years or a gazillion years, or I don't know. We're going to have to just rely on 10 to the power big numbers rather than try and put adjectives on how many zillions we're talking about. So where did we get to before we took this little aside about what is the universe doing? Is it expanding forever or is it going to contract? We said that it took 3 minutes to make all of the hydrogen in the universe, but the hydrogen is running out. Now, stars can live for a long time. Our sun might live for a few billion years. Low mass stars might live considerably longer. A low mass star might live for trillions of years or tens of trillions of years. But stars don't live forever. So what does that mean if the hydrogen is running out? The age of starlight will come to an end. There will be a point at which stars are no longer shining in our universe. When they stop shining, they're still there. We have a whole load of dead stars moving around the galaxy. Gravity still exists, and so even though the stars have stopped shining, they're still orbiting their galaxies. White dwarfs, neutron stars, black holes. It might be a bit odd to talk about white dwarfs not shining, but with no nuclear reactions to keep them hot, white dwarfs are just hot objects. After a while, they will cool down and go dark. In other words, they will become black dwarfs. Some stars will get ejected from the galaxy. Some stars will get eaten by the supermassive black hole, SMBH, at the centre of what we believe is every galaxy in the observable universe. We've mapped out magnetic fields in other galaxies. It's a bit difficult to do with our galaxy because we're inside it, but when we look at other galaxies, we can map out the magnetic fields. We've done that with SOFIA, the Stratospheric Observatory for Infrared Astronomy, now sadly decommissioned. Watch out for it on eBay. It might be going cheap if you want a 747 for yourself. But these magnetic fields have been mapped out, and it's thought that these magnetic fields effectively allow matter to be funneled into the supermassive black hole at the centres of galaxies. Now, what happens to all of the atoms? We know that atoms are positively charged protons surrounded by negatively charged electrons. There's a few neutrons in there as well, but they are not electrically charged. Protons are effectively the positive charge that are holding the atoms together. If protons decay, in other words, if they change into something else, then atoms will fall apart. We don't know if protons are stable or whether they will change. If they are going to change, they are probably not going to change on timescales less than 10 to the 36 years into the future. But we can't be absolutely sure. The timescale we are not sure of. If they decay, they'll decay after this point. Let's for the moment assume that they don't decay so that atoms will continue existing for a little while longer. But even if protons don't decay, atoms will not last forever. Some atoms will survive in black dwarfs, but black dwarfs eventually evaporate via a process which is a quantum mechanical process which I'm not going to describe. So even atoms in black dwarfs will eventually disappear, leaving no atoms left in the universe. We have neutron stars, we have black holes, but neither of those contain any atoms. On a timescale of 10 to the 54 or thereabouts years into the future, all supermassive black holes in the universe will continue to grow. That's because they will hoover up any matter in their own galaxy, and wherever galaxies interact with each other, for instance the galaxies within a galaxy cluster, gravity will pull them together, and when galaxies collide, the black holes at the center will merge, much like the Milky Way black hole and the Andromeda black hole will merge in a few billion years' time. This will happen on a slower timescale for all galaxies in the universe. And supermassive black holes will grow from billions to trillions of solar masses as time goes by. But even black holes are not eternal. They do not last forever. Black holes evaporate, providing that you wait for a really, really long time. We're now talking about potentially 10 to the power 66 years into the future. So let's just have a slide or two on why black holes evaporate. We think that quantum mechanics allows particles and antiparticles to be made from nothing. That seems to happen all the time, so physicists don't really have a problem with that. You borrow energy from nothing and you use that to make matter and antimatter. The matter and antimatter annihilate and you pay back the loan, if you like, of the borrowed energy on very short timescales. So a cartoon way of thinking about that is you borrow energy from nothing, you make matter and antimatter, then they annihilate and repay the energy back again. Let's just see that again. You borrow energy, you make matter and antimatter particles, they eventually annihilate, well, eventually on relatively short timescales, they annihilate and pay back the energy again. What's that got to do with the lifetime of black holes? Well, Stephen Hawking asked himself, what would happen if that process occurred, and we think it occurs all over the place, what if it occurred just outside the event horizon of a black hole? Let's represent that as this black line. If we borrow energy and make matter and antimatter, what if one of them falls into the black hole and the other one doesn't? Now we have a rather odd situation that it looks like a particle has been emitted from the black hole, strictly speaking from just above the event horizon of the black hole. We call this apparent radiation Hawking radiation. Hawking proposed it. We haven't proved it because we haven't seen it, but a lot of scientists believe that this is a reasonable conjecture, a reasonable hypothesis based on our understanding of quantum mechanics. The radiation increases with decreasing mass. In other words, as the black hole gets smaller, the radiation goes up and the black hole evaporates even faster. So what that means is if you watch a black hole for long enough, the radiation levels will increase as the black hole shrinks, and as it shrinks, the radiation levels go up and up and up until it finally disappears in a flash of radiation. On a timescale that's unimaginably large, 10 to the power 80 or 10 to the power 90, even the largest of the supermassive black holes lurking at the centers of galaxies that will merge with each other, even they will evaporate eventually, though it will take trillions of times longer than the black holes that are generated by, for instance, the collapse of a massive star. Have we reached the end of time? Well, we've got to the end of our timeline for sure. Let's just imagine the number 10 to the power 100, a Google. Not that Google, no, that's a misspelling of the original Google. Google 10 to the power 100. It's been calculated that after 1 Google years, the last black hole will have evaporated. In other words, there will be no matter left in the universe whatsoever. Hawking radiation will ultimately just become electromagnetic radiation. In other words, the universe will be full of radiation and no matter. So after this point, nothing interesting happens. And so time becomes essentially meaningless. Yes, the universe will continue to expand. The radiation that's floating around the universe will get stretched out more and more and more and more. Some people call that the heat death of the universe. But with no matter to look at and no people to watch it, nothing interesting at all happens from this point until literally the end of time. So 10 to the power 100, I don't normally do this, but I'll make an exception for 10 to the power 100. Let's just spell it out in full. There's 10 to the power 100. It's 10,000 million, 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 million. You can do it yourself. It's a very long length of time. It is, of course, unimaginable. There is no way we can even conceive of anything of that sort of duration. But that doesn't stop us doing the calculations. We can understand the physics, we can apply the mathematics, we can do the calculations, and we come to these conclusions. The fact that we can't imagine any time like this is irrelevant. We can still apply our understanding of the universe and say, after 1 Google years, everything will have disappeared, other than radiation. Eternity is a very long time, especially towards the end, as said by Woody Allen. I like the quote that came from the XKCD cartoon that tried to put a sort of human perspective on these ridiculous lengths of time. They said, a human is simply a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email a lot. That's one way of putting a human perspective on the existence of the universe and the length of time the universe will exist. Let me finish on a slightly more upbeat note, having said that everything is going to come to an end. Currently, we live in a golden age. The sun is middle-aged and stable and well-behaved. And the moon is at just the right distance to stabilise the Earth's axis and hence stabilise the Earth's season. And as a little bit of a bonus, it also gives us every once in a while the spectacle of a total solar eclipse. Thanks to evolution, we're able to explore and discover and understand the universe in which we live. We're able to do that because we can build ourselves spacecraft, which we can send out into the solar system to visit our nearest neighbours. And we can also build telescopes, which can look out into the universe and see trillions of galaxies at distances of billions of light years. But we would not have been able to do this in the very early universe because we needed to have generations of stars to make the heavier elements. We needed stars to convert hydrogen into helium, to convert helium into carbon and nitrogen and oxygen and phosphorus and calcium and iron, and everything that we need to make us, us. And as we've just seen, if you look to the future, trillions of years from now, the universe will be dark and the universe will be boring. So you could say the best time to exist is now. Thank you.